new topics. We spent sufficient time on that, which is known as first order network analysis. First order network analysis. In most of the standard textbooks, Indian standard textbooks, you will find the topic named transient analysis, which is 100% not correct in the strict sense. We can say also it is correct, but not strictly. Now, what do you mean by first order? Now, the point is this: when I say something like first order, second order, third order, so what kind of thing is coming to your mind? So, when we talk regarding orders, one thing is in control system we talk regarding orders. What is the denominator of transfer functions we say about orders? The second thing is in math course there is a topic called differential equations, is it not? In the differential equation, you used to find two kind of parameters for differential equation. One is what is the degree of that, one is what is the order of that, is it not? So here this concept is something related to that, the order of the differential equation. Now see one thing is clear: if the network is comprises of purely registers, then definitely the equation what we get, that is always algebraic in nature. In other words, that is not differential in nature. So it doesn't matter how many number of register I take or how many number of voltage source, current source I introduce, something like this, and if I write any kind of equation on these things, whether it's nodal or mesh, something like this, it will always look like an algebraic equation. When I say algebraic equation, means the equation should be in these formats: ax plus by plus cz equal to d. In other words, if the network is purely resistive, you cannot get something like a into dx by dt, b into dy by dt. You will never get like this. Why you will not get like this? Because Ohm's law for resistor is an algebraic equation. B equal to IR is an algebraic equation. If the equation would have been V equal to R into di by dt, obviously all this equation would have been what? They would have differential in natures. So that's why in the resistive networks, we can say those are the zero order networks, because the differential equation order is zero, because there is no existing at all. But the point is that we understood in the case of inductor and capacitors, now the voltage and current in case of L and C, they are no more algebraic like the case it is in the resistor case, because V equal to L d by dt, I equal to C d by dt. Now the kind of equations when we handle, they are no more algebraic. They are what? They are differential in natures. In other words, what I want to tell is, if I take a simple RC network like this, or a RL network like this, okay? So if I say that the voltage is Vs, and let's assume that the current that is being passing through this is something like Is, so this is R and this is L, then the Vs answer is, it is Is into R plus L dis by dt, is it not? Because by KVL, so this is the drop like this voltage is by Ohm's law current into this voltage is L dis by dt. So I want to tell the equation what you are handling here is no more algebraic in nature. This is what? This is differential equations. And when I am specifically given the name here, first order network analysis, the meaning is that in this entire topic, whatever discussions we will do, those are valid for the first order differential equations only, right? So which will, like, what is the order of this? This is of course 1. If you remember in the math class, I might have told you what is the highest order of this. Means what if it would have been d square by dt square, I would have said that order is 2. So all our analysis in these topics are based on the first order network only. So which equation is always a what? It will be the first order equation. Now what equation is it? Any equation you take, whether you write any nodal equation, whether you write any mesh equation, whatever you write the equation, you will never get a second order equation. At max it can be first. And also, I mean, that's what the questions we are getting in the gate. Almost, I can say 99.99% of the questions from these topics are based on the first order. Of course, there is for second order also some questions are there. Those are very less. And I'll also tell you how to handle that. And third and fourth order questions will never get in the gate exam, because if it is a third order and fourth order equations, the one question itself or not more than 2 to 3 questions is sufficient to spend all the 3 hours of time in gate exams. In other words, calculation will be too much complicated that they will never ask that. That's for sure. By the way, what is our goal in this case? The goal in this case is Any network what we are solving so far, what we are doing in every case, network is given, we are always finding some current, some voltage, those kind of things, is it not? So here also our objective is that only. So some network will be given with RLC, and they will ask us to find the voltage, find the currents, like this they will ask us. So ultimate aim is, if I ask you find the current IS here, then what is the ultimate aim here? So that means solve these differential equations. The only change I am doing with respect to math course is, in math course we are dealing with dy by dx, y and x notations. But here only we are dealing with voltage current notations and RLC notations here. So the same mathematical approach here also, but our visualization is little bit different compared to the math course, right? Because we are engineers, we are not math people. So we should see this and we should handle the solution of this in the engineering analysis tool, not by the directly mathematical tool itself. Okay, so what is the order of these networks? The order of this network is first order. Why first order? Because I will never get a second order equation on this. Okay, please reply. What is the order of this network? If I introduce a RLC like this, then what should I say at this? What is the maximum order you can get? Or if you write the Kcl equation for these, what you get is the voltage across capacitor is given by 1 by C integral I dt, right? And in the math class, I am pretty sure you have learned this kind of techniques. Like if the equation is given like this, how do I find the order of this? So your sir might have said you differentiate this equation one time, left hand side and the right hand side. If I differentiate it one times, obviously this integration will no more exist. And here I will have a d square by dt square terms. And this is di by dt. And obviously the answer will be 2. So that is second order networks. Is it not? Yes, that has to be second order. So many of Hari, Samiran, all are replying it is 2. So it has to be second order networks. In fact, so a series RL networks, what will happen if it is a series RC network, by the way? If it is series RC networks, you have this term. But still it is first order, because when you differentiate this equation now, you will have only one di by dt terms. And that's of course is first order networks. So a series RC or series RL or parallel RC or parallel RL, they are first orders. And of course, there won't be any change in answer if I connect them in terms of what? By parallel combinations, right? If I say this is what the case is, and I'm connecting something like current source and all, so you can see that the current equation here, if I write it, it will be again first order networks. Because if I say the voltage is V, then if I say this is I, so I equal to V by R plus C into dV by dt. And you can see that this equation is again first orders. You take the RL parallel also, you'll be again resulting with the same first order networks. You'll never get second, third like this. So the question arises, how do I identify whether the network is a first order networks or second order networks or third order networks? One approach is you go this way, right? But the situation what I am handling here is pretty simple in this case, because it's a series RC RL. But what if you have so many combinations, a bunch of resistor, bunch of inductor, bunch of capacitors? So that is not that easy in that case then. Then we should know the efficiency or the trick. How do you identify that? And the trick is this, like you simply observe how many number of non-separable amount of elements are there, the energy storing elements. In other words, how many number of inductor and capacitors are there in the networks which are non-separable. The meaning to tell you this is, what I want to tell is, okay, see this. How many number of energy storing elements are there? 1. Energy storing means L and C. How is the answer? Here it is 1. If I introduce the inductors, so without writing the equations, how many number of energy storing elements are there? 2. And don't mix L and C. However, if the situation would have been like this, like let's say that I have a voltage Vs, okay, which is something like this, and this is R, and this is C, and this is R, this is C, and this is R, and this is L, and again this is some R, this is C, and L, something like this. So let's say this is C1, this is C2, this is L1, C3, L2, and like this if it is. If I ask you what is the order of these networks, then probably your answer should be how much in this case? The answer should be, I should directly count it. 1, 2, 3, 4, 5. So I will say the order of this network is 5. That is the simplest approach. Count how many number of elements are there. But I have used a word, number of non-separable element. Meaning is that some of you can make an argument with me that if this is C, Why you are saying it is first order networks? I can say that this is C by, okay, so I can say that C by 2 and C by 2 are connected in parallel like this. And this is the case, if it is C by 2 and this is also C by 2, then the equivalent is C. Then I can say that again, because two capacitors, the answer is 2 here. So that is a wrong analysis. So that's why I use the word non-separable. You cannot reduce that further. So can you reduce it to by applying some combination? Can you reduce it? It's impossible. We cannot do that. Right? So that's what the point is here. So let me write down the statement. The statement is this. The number of non-separable L and C elements in a network represents its order. Since, what is the reason behind this? Since that is the maximum order of differential equation which is possible. Now someone can make an argument. Why you are saying it is 5? I can say that, okay, so the register is there, I write the equation V equal to IR. That is not the argument. The argument is, what is the maximum order of equation you can get? It will never exceed 5. Right? It will never exceed is 5. So the answer is 5. And in fact, if you are good in the, the concept of controls and all, where you might have done how to find the transfer function of some networks. So you might have seen in the denominator the s power 5 terms used to come. So what does that means? That what is the highest order of the power of s in the denominators, that represents the order of that. So if you find the transfer function of this, it has to be 5. Okay. So that's what the meaning of order of the networks. So as I said, I have given the heading itself, first order. That means we are not going to see this much of big networks in our course. Because if that's what the problem is, even in the IS 15 mark also they will never ask this. Because if this kind of question comes, then 2 to 3 questions are sufficient to spend 3 hours of time. So that never happens, right? So second order also there are some standard model problem they are asking, which you can easily answer by look itself. So we'll see only 2 categories, first and second order networks. So that's what the definition of this. Okay. Now the point is this, what is the meaning of analysis? Right? So as I said, we understood what is the meaning of first order networks. Now what is the meaning of analysis? In the first order day itself I said the difference between analysis and synthesis. When the network interconnection is given and we are asked to find the response, either the voltage or currents, right? So we say that these problems are based on the analysis model problems. Now when I say it's the RL network or RC network is given to you, what might be our interest? Our interest might be to find the capacitor currents or capacitor voltage or inductor current or inductor voltage. Some current and voltage is needed to find. And of course, because I am embedding the resistors with the inductor capacitors, it is no way surprising the equations will be always differential in nature, or mostly it will be differential in nature. So finding the solution of the first order network means solving the differential equations, because the resulting equations, the KVL cases will be by default differential. So find the solution of current and voltage means solve the differential equations. So the network problem, once you have written the KVL and KCL, the problem is converted to a mathematics problems. Is it not? So here I am writing that point also. So solving the first order networks or analyzing the first order networks. Analyzing the first order networks, analyzing the first or second or third order networks means solving the differential equations. Solving the differential equations. Okay? So in the entire topics, I will teach you how to solve the differential equations. But in fact, we are never going to, to see the things the way you are learning in the math class or how are said in the math class. A lot of things, exact differential equations, Leibniz equations, Euler equations, and what is that? Wronskian, what is that? Complementary functions. Lot of things you have learned in the differential equation in the math course. But that's what not the things we are going to talk in our class. We need what we need actually, so that is very much specific. And some of the authors, Indian author books, they are solving those problems in a lot of complicated ways, but that's not needed, right? So we'll see how to do this. Now the problem is this. Let's say that I'm getting one equation. Let's say the equation is di by dt plus r by L into it is equal to Vs. Let's assume that the equation is like this. Now I ask you, find the solution of it. I ask you, find the solution of it. So how do you get the solution of this, right? So there are so many approaches to solve this problem. One of the approaches, you go by the mathematical approach. But because it's a differential equation, it is no more surprising that there will be some kind of initial condition. In math also you have studied x of 0 equal to 1, sometimes like they give like this. And network case, initial conditions are very frequently things, because the inductor capacitors definitely will have some kind of initial current inductors capacitor most of the cases. So the differential equations what I am writing here, this is having non-zero initial conditions like x of 0 equal to 1, x dash of 0 equal to 2, like that you have studied in math course. These kind of situations also we are going to handle in our case. So we are going to deal with a differential equation whose initial conditions are non-zero. So how do I solve this? So if I ask this question to a math faculty, or if you are a student of math class, probably you will say that the solution of the IT will comprise of two parts. What are those two parts? If you remember, one part is complementary function solution, right? Another part is particular integral solutions. If you remember in the math class, right? Sir might have said you the solution of the differential equations that comprise of two parts, complementary and particular integral. We find the complementary function separately and we find the particular integral separately, and when we add both of them, we find the total solutions. That's what we did in the math class, if you remember. But what is the meaning of complementary functions? How do you find this and how do you find this? So complementary function is obtained by making this term as 0. So that is because of the initial conditions. If you see that most of the answers used to be in the C1 into e power minus 2x kind of terms. So this is because of initial conditions. And in our course, this is the contribution of the external signals. External signal. What is the meaning of this? Initial condition means if this the inductor's case is there, so I will say that it is I of 0 minus is there. External signal means Vs. Anyway, I will take these things in more depth. The pictures will be more clear in that time. But this is what the approach you do in the math approach. But this is not a efficient techniques that how we solve the problems, right? So what is the efficient technique then? As far as engineering is concerned, the best tool to handle the differential equation is Laplace Transform approach, right? And I don't know how many of you have studied this topic in the math class or in your BTech days, and Laplace, some people feels it is tough. See, I will tell you, the things are not developed to make the things complicated. Some people think, even including me when I was a student, phasor is a very tough thing in networks. I will show you, if phasor would not have been there, how complicated the networks problem would have been. In fact, in the Hate came early, there are 3 pages he has given, like where he has illustrated what is the importance of the phasor. If phasor would not have been there, how much complicated the thing is by solving the problems in the normal mathematical approach. Things are not developed to make the situation complicated. So there is a problem to handle the situations, so the things are simplified. And Laplace is one of that. Laplace is not tough. Laplace is the easiest topic. I mean, as far as differential equation is concerned, right? Actually, when I say Laplace, right? So there are 2 particular applications of this where Laplace is used. There are so many, but 2 particular approach. One of the thing is the differential equation, right? Converted to what? The integral differential equation. One of the popular application is the integral differential equation converted to algebraic equations. I will show you how it is happening. Or you might have studied in the math course also. And the second thing is convolutions become multiplications. But convolution is not a topic in the networks. You learn in the signals. Convolution becomes multiplications. There are so many, but these are two popular things. Why Laplace is very much popular? Because in control system, I am pretty much confident you have learned these techniques. Like if the transfer function is g of s, and if the input is x of s, output is y of s, you write that y of s equal to g of s into x of s. Is it not? Like when you find the impulse response, step response kind of things. So, in other words, what you are saying is, this is multiplication of this and this. But how it is happening? But actually, if I assume that it's a LTI systems, the actual equation should be yt equal to x of t convolve gt. But evaluating the convolution is a very time consuming process. And complicated as well, if the signals are complicated. But when it comes to, because why it is complicated means I have to deal with the integrations there. If you remember, the convolution integral is given as x of tau h of t minus tau d tau. And again, finding the range integrating is really complicated. But once you are dealing with this, if you find the Laplace of this, so that becomes x of s and h of s. And we are pretty much comfortable to the multiplications. And in signal course, you will learn all those things, how it is happening. So that is one more great advantage of that from signal system point of view and from control system point of view. But from maths point of view, this is what the great thing is converted to algebraic equations. Okay? And in fact, we are not going to see the solution of the differential equation by this approach. We are going to see the solution of differential equation by this approach. Where the major advantage of Laplace transform equation is, when you solve the differential equations, you don't have to find two separate solutions. In the maths, you are finding this solution separately and this solution separately, and you are finally adding that. But in this case, that's not the case. It doesn't matter. Only one equation done. So that's what the great advantage of Laplace. And in fact, we are going to solve the problems by using this. And in fact, some of the Indian author books, they're also solving by this approach. But I'll never suggest go by that methods. Because you'll feel like you are not learning networks, you are learning some math again, right? Which is a boring part of course, I feel. Okay? So, here I am writing this. Solution of differential equation by normal mathematical approach. Solution of differential equation by normal mathematical approach is time consuming and complicated. Someone asked, why you are going for Laplace? The reason is this, it is time consuming and complicated. Okay? Once I will show you one problems, you will feel it's not like a theoretical statement like this I am giving. So, we are going for Laplace transform approach. So, we are going for Laplace transform approach. Okay, now let me tell you some basics regarding the Laplace transform analysis. See, the Laplace transform, there are two kinds of Laplace transform actually. In the signal system course, you learn all these things. One of the Laplace transform is known as unilateral Laplace transforms. Another one is known as bilateral Laplace transforms. If I have a signal x of t, the Laplace transform, this is obtained by x of s. While evaluating the x of s, if I use the integral 0 to infinity x of t into e power minus st dt, so this is known as unilateral Laplace transforms. The only change is if I make the integral not from 0 to infinity, but minus infinity to infinity, so that becomes bilateral Laplace transforms. The application of unilateral Laplace transform is, the first point is this. Okay, this is the only point we need in our course. The application of unilateral Laplace transform is, it is used to solve differential equation with non-zero initial condition. We need this because our inductor capacitors, they will make us to follow this one with non-zero initial conditions, right? That's what you did in the math class, and math, refer any of the books, they will give this one, you will not find this one in the math. But all signal system book you see, you will find this, very rarely you will find this. Most of the discussion is this. Why is this? And this is used for LTI system analysis. And what is the meaning of LTI systems? Like the concept of causality, stability, etc. We used to find it from the bilateral Laplace transforms, right? In signal you learn all these things. One more point is, when we discuss regarding Laplace transform, we talk regarding the region of convergence, ROC. So here ROC concept is used, but here no ROC concept. Why no ROC concept? Again the topic of signals, right? So these are two major points regarding unilateral and bilateral Laplace transform. But as far as network is concerned, we are going to talk about this, not this. This is the topic in the signals. Okay. So I am just giving you the necessary stuff that is needed for me to teach this transient topics. Laplace transform itself is a more than 4-hour topics in the signals. You will study all those things there in signal systems, I will tell you. But let's talk regarding, take a heading, review of Laplace transforms. Review of Laplace transforms. Okay. So this is review, of course. I have not written Laplace transform. That means I am just going to give you some necessary properties and the stuff what we need. Okay, I have given that thing. So first thing is, any signal x of t is there. So its Laplace transform is for our subject only this. Some of the useful property that I need is one of the properties, if the signal x of t is there, right, that is property number 1. If the Laplace transform is x of s, the time shifting property says that the Laplace transform of this will be this, x of s into e power minus st naught. Second property I need is the dxt by dt. That's the most crucial properties because our inductor capacitors, they satisfy this kind of relationship, which is s y s minus y of 0 minus. Sorry, if it is dy t by dt, I should use y notation, right? Third one is, what will happen in the second order case? Well, nothing change. It is s square of ys minus s y of 0 minus minus y dash of 0 minus. Notice one thing, that if this term is of first order, you need one initial condition. If it is of 2, you need 2. If it is 3, you need 3. If it is n, you need n initial conditions. Okay? That's what one things. And some of the standard things we need. The standard thing is this. Impulse signal is denoted by delta t. Its Laplace transform is 1. Any transform of impulse is 1, like the Fourier transforms, the Laplace transforms, the jet transform, the DTFT, whatever the transforms are there in the signals, all transforms are becoming 1. This also question in the IS. Okay, so signals I will tell you in the signal class. And another one is, if it is step signal, UT, so this Laplace transform is 1 by s, which we need. Another thing we need, that e power minus at is 1 by s plus a, right? Where a I am assuming, of course, it is positive. A is positive, so it is 1 by s. Like e power minus 2 will have 1 by s plus 2, that kind of things. What else is needed? Sometime ramp signal is not needed. R of t, or which is known as t into ut, right? This is given by 1 by s square. What else left? Yeah, and one more thing is, if it is sine omega naught t, sometime this is needed. It is omega naught by s square plus omega naught square. If it is cos omega naught t, it is s upon s square plus omega naught square. Next point is, if it is e power minus at cos omega naught t ut, right? Using the, okay, there is one more property, which is exponential multiple property. But anyway, so what happens is, and what that property says is this: if you can take down this x of t having Laplace x of s, then x of t into e power s naught t will have Laplace x of s minus s naught. The meaning is that if x of t, you know the Laplace transform, if you multiply a factor e power s naught t in the time domain, in the s domain wherever s is there, it has to be replaced by s minus s naught. Now the point is, I know that sine cos omega naught t having this is the Laplace. If I multiply a e power minus a t on this, what the Laplace transform will be, wherever s is there, replace it by s minus s naught. That means in this case s plus a. So this becomes s plus a divided by s plus a whole square plus omega naught square. Similar way, if I ask you what is for e power minus a t sine omega naught t ut, right? So that becomes only here is the change. So this omega naught by s plus a whole square plus omega naught square. So that's what the thing is. And one more thing, like if we deal with any constant, like some constant k, the Laplace transform is k by s. Why it is k by s means, because the Laplace transform of any signal I define like this, if it is constant, right? If I integrate that constant, so what will get? 0 to infinity, and this is k into e power minus st dt. So k is a constant, that is k into e power minus st divided by minus s, and this is 0 to infinity. So when you substitute here infinity, that becomes 0. So it is k by minus s, this is e power minus st, and this is infinity to 0. So which is k by minus s, and this is 0 minus 1. So that minus 1, this is cancelled, and that becomes k by s. Right. But of course, if I say this limit is minus infinity to infinity, then it don't exist. Then the ROC concept will come into picture there, which is bilateral Laplace transform case. That's not the discussion here. So we should talk regarding only 0 to infinity in this case. Okay, that is sufficient for networks. You don't need anything else beyond this. Let us see some application of this from network point of view. So take down this Laplace transform model of RLC. Okay, RLC. So how do I do this? Okay, so coming to the, let's start with the capacitor. Because we said IC equal to C VCT by dt. In other words, if I take, so this is these things, if I take Laplace transform both sides, x of t having x of s, so ICT having IC of s, and we use usually the capital letter for Laplace case. And c is anyway constant, I am keeping outside, right? So what is the Laplace of this? What is the Laplace of dx by dt? Dx by dt Laplace s into x of s minus x of 0 minus. So if this is what the case is, so what should I write for this? So s into VCS minus Vc of 0 minus, because the property what I said, dy by dt having what? S into I of s minus y of 0 minus. So wherever dv by dt s into VCS minus Vc of 0 minus. So which is SC VCS minus C Vc 0 minus. If this is what ICS is, right, I can say that VCS, if I ask you what is VCS, so I can say that it is 1 by SC into ICS plus Vc 0 minus by S, right. You bring this to this side, so which is C Vc 0 minus, and divide SC in both terms. That is 1 by SC, and if you divide SC, C will cancel, so we will be resulting with this. So IC of S, right. So the equation which look like this in the time domain case, the equation look like this in case of Laplace domain case. If I want to show this by a circuit model diagram, how it will look like? So it will look like this. So By the way, is it a KVL or Kcl equation? KVL, because voltage terms are added means it is KVL. And because I am adding the voltage, when voltage will be added? When they will be in series. When current will be added? When they will be in parallel. So a capacitor which look like this only in the normal case, having some initial condition Vc 0 minus. So how it will look like in case of Laplace domain is this. So because of the first term, so it is like some I into R kind of thing, you are getting it right. So what I am saying is it should be 1 by SC, and again I need one more term. So I am modeling that by this Vc 0 minus by S, which is a constant batteries. In other words, if the initial condition is 0, this is 0, and this is 0 means this is a short circuit, right? So it will be a perfect capacitor which will satisfy VCS equal to 1 by S into ICS. So this is what the circuit model of this. So we should say that this terminal voltage is VCS and this current is ICS. Okay. And again I am reminding you, when someone asks you to find the capacitor voltage, you should not confuse to find this voltage. So when I say capacitor voltage means this and this, because this initial condition is also a part of this. You should include this as well. It's not like that you are finding only, that is a wrong thing. Okay, this is one model. Another model will be like this. Okay, some of you might be, okay, that is one thing. I can apply the source transformation to this. If I apply source transformation to this, how does that look like? So it will look like this. So I will have a current source and I will have a capacitors. So like, you know, like when the voltage source and resistors are in series, when you do source transformation, the same resistance comes, or the same thing here comes here 1 by SC, and what will be this? Like that it is V by R. So this by this. So S will be, you know, in the SC will be in the numerator, so SS will cancel. So this value is CVC 0 minus, the current source values. And we should say that this is what VCS is, and we should say that this is what ICS is. And ICS is of course this. How it is? Of course this I am saying this. See this equation. What this equation indicates? ICS is equal to, right? If this is VCS, right? So what is this current then? This current is VCS by this, which is SC into this. And that should be equal to, because if it would have been downward, right? If the current direction was downward, I would have said that it is CVC 0 minus plus this. But because it is upward, so we are getting a negative sign here. So both of these models are valid for the capacitor case, right? This is also a great question. You can check it out. Which of the following the correct Laplace model of the RLC they have asked. I mean for the capacitor they have asked. What about for the inductors? And in fact, it's not like that for the questions only, because I'll use that questions these models while we'll solve the problems. So take care about that. So coming to inductor case, we said VL equal to L dIL by dt. Again, if I apply the Laplace transform, VLT equal to L dIL by dt. So I should say that VLS is equal to L into which is SILS minus it is IL of 0 minus, like Y of 0 minus we use there, which is SLILS minus LIL of 0 minus. So this is what VLS is. Now what will be ILS then? ILS would be equal to 1 by SL into VL of S plus L, if I bring it to this side, by SL. That means IL of 0 minus divided by S. Because if I bring it this side, so again if you divide SL, LL will be cancelled, you will have only S. So let us draw these two diagrams as well. So inductors, which is L with initial condition, we usually write it is IL of 0 minus. If I model this equation, how it will look like? So this is a Kcl equation because current terms are being added. So I mean there are two current terms are added. So this I have to model this. So I am saying that this is like this, and I have a inductor like this. So if I say that this voltage is VL of S, this current is IL of S, and this current is IL 0 minus by S for this one, right? And this is what S of L. So that if it is SL, the current will be voltage by this. So that the current is VL by SL. So it will satisfy this, and for this is the case. And how do I model this case then? I mean, for these equations, it will be series because they are KVL equations. And how it will look like is, it is SL and a battery minus plus LIL of 0 minus. And this is what the VLS, and this is what the ILS. Because it will satisfy this SIL, and because if the polarity is like this, then only the negative sign will come into picture. So take care. So you see the polarity here. So this is, and they are different, and these are also opposite to each other. So there are two possible model, or in fact, if you do source transformation to this also, you will get this, because you can see I told source transformation wherever the arrow direction is pointing, that should be plus. So if you multiply this, SS cancel, that is this, and inductor is same thing you are getting in series here. So both are equally valid, but popularly we use this for inductors and we use this for capacitors. There is nothing wrong if you use this and this, right? But popularly most of the books they follow this. We will also be talking about that mostly. What about the inductor? The resistor? Resistor case, there is no change because it's the algebraic equation. Bt equal to R into IT. So B, okay, R of S is equal to R into IR of S. So the point is, when I say this is Vt, this is It, this is R, so there is absolutely no change. This is R, this is VR of S, this is IR of S. So these are the circuit model, right, of R, L and C in the Laplace case, right. And don't be scared like we are going to use big Laplace partial fractions. It's not like that. First order means it is very simple. I have to make of course two derivations and some theoretical analysis is needed. And some terms are there like natural response, forced response, steady state response. All those, the terms I will explain you with the help of one examples, and we'll understand what does this means actually. And once we have grip on that, so all the problems very easily we can solve the way we are doing so far. Okay? And again I am reminding you, when I say current of inductor, don't think this current. That is this and this. I mean initial condition is also part of the network, right? So one derivation is needed, which is of actually one observation problem is there, how to make you feel that Laplace transform is easy compared to the math approach. And that itself I will explain you the concept of the natural response, forced response, transient response, steady state response, which will take another 15-20 minutes. And immediately followed by that, we'll switch into the series RC and the series of parallel RL first order networks, and we'll derive some formula and we'll do some analysis from where the theoretical analysis also are getting a lot of questions. And after we generalize to formula, like I'll tell you what are the formula. We need this formula. VCT is equal to VC of infinity plus VC of 0 minus VC of infinity into e power of minus t by tau for t greater than 0. IL of t is equal to IL of infinity plus IL of 0 minus IL of infinity into e power minus t by tau for t greater than 0. So these two formula we need, and based on which almost 99.99% of questions are coming. But we need to interpret how it is coming and how to use this, right? So this is what the objective, and to reach into this formula, it needs minimum 2 hours of time.